Okay, so let us continue with the magnetic induction. And this gives us the route to look at what is inductance, which is the counterpart of capacitance in electrostatics. And then we'll look at magnetic energy, okay, through this route of understanding inductance, 8b2. Before I go there, I should have done something in the last lecture itself, which I would like to do now, is flux rule and Faraday's law. So let's take an unified view. We have done here motional EMF first and deliberately, okay? And then I did Faraday's law to tell you that there are two different reasons for the same law of the flux rule. So let's take a unified view to remind you, okay? So we have seen that Faraday's law in different forms for time varying magnetic fields. Okay, we have seen that. So that is del cross E minus del B by del T. We just derived it in the last lecture. And so the EMF, you could see its expression in experiments through EMF, that E dot dl, and that you could calculate from the total time derivative of the magnetic flux. All right, and this is, I could express this as E dot dl, okay, or EMF as a source term changing through the dA. But here, remember, this is the total derivative of phi, that's the flux rule. And this is the partial derivative, that is explicit dependence of B as a function of time going through a surface, a well-defined surface. So these are the three forms in which the pure form of Faraday's law that we have seen. All right. But we also have the EMF generated by the motional EMF in a magnetic field, where even if the magnetic field is not changing, if there is a motion of the circuit, and that we attributed to the Lorentz force. Okay, so the flux rule involving total time derivative, okay, is valid for both mechanisms. That is for uh, time varying, for both time varying B and moving circuit. All right, so we can say that the electromotive EMF is minus d phi by dt is a rule which is true for both mechanisms. That's what I'm saying. So this can be stated even more explicitly, okay, as a combination of two mechanisms generalized as, that is this E, instead of total time derivative, I can express it as this, which is the Faraday's law, pure Faraday's law, and the motional EMF V cross P dot dl. Okay, one can derive this explicitly also, but I don't think in our case we need to do that. We already seen this EMF V cross B dot dl, and this is, but this is partial derivative. Okay, of course, in this both are included. Okay, so both methods can be used to solve problems on, okay, whatever the all kind of cases when motion through time varying magnetic fields. Okay, so here we are talking about only the time varying magnetic field, but suppose there is a circuit moving also, okay, and there is a time varying magnetic field, then of course I can use this because this is a total time derivative. I can look at the net flux change because both because of movement and because of time varying. Okay, but if I want to look at the contribution or the time varying magnetic field separately to the EMF and because of the motion, okay, then I could, the answers to the two would be the same in both cases. They're equivalent. All right. So we have three methods really: del cross E minus del by del T. Okay. E through total time derivative, or E through, okay, this is EMF and here is actually E calculation. So motion through time varying and spatially varying magnetic field. You can have both, right? Then of course, both these methods would work. Okay. You can have a moving non-expanding circuit, which is normally one arm was moving in your on rails, so that is an expanding circuit, but it could be a circuit which is not expanding. So area is the same, but it is moving, okay, or is a rotating, okay, all that. So all cases are covered by this. Okay, but to be able to see explicitly that they come, a part can come from explicitly from the changing magnetic field and because of the motion. Okay, I just wanted to make that summary as an unified view. Okay, so now let's go to mutual inductance. Okay, and which is what is called the reciprocity theorem or the Neumann formula. All right, so let's take the loop 1 and loop 2. So if I run a current in loop 1, it's going to produce a B1, okay, which is going to cross loop 2. All right, and hence there is a flux cutting because of loop 1 in loop 2. Okay, so okay, so phi 2, ignore this. I don't know why I wrote that. So phi 2, the flux going through this loop, phi 2 is B1 dot dA2, right? So if I take a small area dA2 here, and then there's the flux of because of B1. Okay, now note that both A1 and B1 are proportional to I1 in loop 1. Okay, so that is the vector potential A1, okay, and B1 are proportional to I1 in loop 1. Okay, why? Because we know by Earth-Sever's law, okay, which is dl cross r square, and that is B1 is proportional to I1. Similarly, if I write down A1 is also proportional to I1. If I'm moving an I1 here, so this is dl1 by r. R, of course, is from any dl to the other part in the loop. So that is my curly R. All right. So, but what is important is B1 and A1 are both proportional to the source current I1. So if I now look at phi 2, okay, which is B1 dA2, I can, so whatever be the integral, okay, so that's a I1 I have taken out, and hence this depends only on geometry. The R square and R, these are only the geometrical factors. dl1 cross R hat or dl1 over the loop, these are all geometry. And hence phi 2, the flux going through loop 2 must be proportional to I1, and that proportionality constant I can, which depends only on the shape and the geometry of how the two loops are aligned in space. All right, so that factor, all this integral involving is a proportionality factor depending only on, and hence the flux is proportional to the current running. Flux in 2 is proportional to the current running in loop 1, and that proportionality factor is called the mutual inductance. Okay, so where M21 is the proportionality constant, that is the phi 2 because of 1. Okay, so 1 is the current source and 2 is where the magnetic flux has been produced. So 2 1, right, where M2 is the proportionality constant. Now phi 2 is, of course, I can write down in terms of del curl of A1 that we know. So B1 I'm replacing by curl of A1, and that is also M21 I1. All right. So this I can write down as, I can convert, okay, from a surface integral to a line integral, invoking Stokes' theorem, of course. And this is over the loop dl2. Okay, so if I take this is dA2, okay, so if I take A1 over dl2, all right, then I'll get the phi. So phi, so that's a flux being related to the vector potential, okay, vector potential of the source, okay, going through the, so line integral of the vector potential is the flux, the magnetic flux through it. It's very important consequences, okay, but it's simply derived. So mu naught 4 pi, okay, so I can just replace, I'm just replacing by that. Of course, this is again proportional to, I'm just replacing by A1, so integral, so there is already an integral, and dl1 and dl2. All right, so this is A1, so phi 2 is then proportional to, I just replaced by this, and then one can say that M21 is, okay, is proportional to mu naught 4 pi. Okay, so this is, I've just taken out I1 out of this. Everything else is geometrical. Okay, so M21 that I was trying to define, I could define in terms of geometry. There is double integral over dl1 dot dl2. All right. So this is of not much practical use, but one can see where it is coming from. All right. Um, so this is called the Neumann formula. Okay. So this is for both integrals. This is the geometrical factor, which is the mutual inductance. So M21 is purely geometrical. I've been saying this. Let me write it down. Okay. Geometrical quantity. M21 is, of course, M12. There is dl1 dot dl2 involves. Okay. So this could be dl2 dot dl1, and this will be the same. All right. And hence, I need not say from which is the source and where am I calculating. So mutual inductance is simply M. Okay. M21 is equal to M12, which is M. And then, which is an important insight, that irrespective of the shape and position of the loops, the flux through 2 due to I in loop 1 is equal to flux in loop 1 if we run the same current in loop 2. So this is sometimes go by the name of reciprocity theorem. Okay, that is, if I run I in here, then the flux here, okay, is the same. The flux is the same if I run I here and the flux, okay, because M is the same. Okay, and this can be taken advantage of in solving problems. Okay, in some problem, it may not be possible to calculate the flux over one loop. Okay, but the reciprocity theorem allows that make the same current flow in the other, okay, and measure the flux uh, in the other loop. All right, I'll illustrate that, but that's an important, that sometimes goes by the name of reciprocity theorem. I'll give a problem in the home assignment to do that. So we have seen mutual inductance, but that could be any circuit. It need not be two loops. Of course, loop 1 and loop 2. That is, we have seen that the EMF is now depends on minus d phi by dt, and that should be minus mutual inductance di by dt. Okay, this is how we use in our transformers the rate of change of current. Okay, EMF, and that is the two loops are connected to the mutual inductance. So M is equal to, you can think of physically as a flux in loop 2 due to a unit current in loop 1. Okay, that's to the flux route. But you could also think of that M is an induced EMF in loop 2, okay, for unit rate of change of di by dt. Okay, so you could think of M is sort of divided by unit rate of change of current, right? Okay, so in terms of flux and in terms of induced EMF, both these pictures one can have in mind. Okay, that was phi was equal to mi, and E is minus mdi by dt. And unit of inductance is 1 Henry, 1 volt second by ampere, which is nothing but flux by current. Flux is, of course, Weber, current is amperes, and this Weber is nothing but Tesla into area meter square by amps. Okay, so that's 1 Henry. 1 Henry is quite a large unit of inductance. So a change in current, okay, not only just change in current induces in the other loops, but in the change in current, suppose I have only one loop, okay, and then change in current also induces an EMF in the source loop itself, right? So the field, therefore, also the flux is proportional to the current for that particular source loop itself. So I could say that source loop phi is equal to Li. So even if there is only one loop and I run a current I, then there's an associated flux with it. Okay. So since there is no other loop, instead of mutual, I called, so phi flux is proportional to the current I. And that constant of proportionality is called the self-inductance. Okay. So E is equal to minus d phi by dt minus L di by dt. This is actually for a circuit element of any L, this is the definition of the EMF. EMF E is minus L di by dt for even for a single loop. So, and of course, this minus sign, remember, opposes the change in current. Okay, so it doesn't like change in current. And so this is exactly like Lentz's law. It doesn't like the flux to change. Okay, and hence it doesn't like change in current also. And that is why it calls back EMF. Okay, so it's a self-inductance. Okay, and you have to fight this EMF to change current in any loop, in any circuit. Okay, and hence it's called the back EMF, as if you have to fight that EMF to change any current. Okay, especially for a let's say here I deliberately was not talking about any particular element, but in general a loop, a circuit loop. And so this is a solenoid, and if you want to change current in this solenoid, then of course you'll have to face the back EMF, all right, because there will be flux linkages through the so there will be a self-inductance of any circuit element, and of course of an inductor, which is a model inductor with a model of inductance as a true inductor. All right. Inductance is something like mass is the mechanical analog. In a larger the mass you require, it is harder to give it a velocity, right? So exactly similarly, this is larger the inductance, it is harder to change the current in an inductor, for example, or in any circuit. All right. There is an equivalence, about the capacitance as a spring and inductor as a mass, and what the force there is a potential here. Okay, and whatever is friction in a mechanical system is the resistance in the electrical system. There is a formal analogy. You can set up the differential equation in an LCR circuit, which exactly look like the mass spring system with friction. I am sure you know about this. Okay. Let's see, find the self-inductance per unit length of a long solenoid of radius r carrying n turns per unit length. And that's something very easy to do. So I know phi is equal to Li. So B is equal to, of course, mu naught Ni. Okay. I'm not writing down the vectorial form. We have done it enough. For a single turn, then the flux is mu naught Ni and pi r square is the area. Okay. So the flux cutting a single turn is, what is this? For a length, any length of L, of course, then there would be how many n turns per length and unit length. So there will be number of turns will be n into L. Okay. So the total flux will be mu naught Ni pi r square n into L. All right. So self-inductance then can be calculated, self-inductance per unit length. Then I can calculate as simply phi is proportional to I. And so unit length, I'll take L out. And so L is mu naught N square pi R square. So self-inductance per unit length of a long solenoid is, of course, I'm using this B, which means long solenoid. I'm neglecting the ends and that there is any magnetic field outside. So self-inductance per unit length. And so remember that there is a square dependence of n turns per unit length. Also a square dependence of the size of the solenoid. All right. So the back EMF depends on L. Okay. So if you want to change current, then the size, and if you change N, okay, you could change N to get more magnetic field. Okay. But then the rate of change you can change will becoming harder by square. Okay, you could link more flux. You could be making the size of the solenoid larger, but then you would be paying in terms of square, in terms of inductance. Okay, that's important. It's a simple derivation, but it's in a very important formula in on practical workbench. All right. So this is important in design constraints. Okay, for example, stronger magnetic fields, okay, you can get at the cost of larger back EMF. Okay, you want to get stronger, then you make n turns, many more turns. Okay, and then you would be paying in terms of the working against back EMF in setting up the current. That's an important design constraints while designing winding inductors. I hope you have tried your hand at winding an inductor. It's so simple to do. The copper wire is easily available, and take a particular cylindrical shape and turn it, and you can do many experiments if you take care of back EMF. Actually, back EMF can be very nasty, can give you a shock if you don't do it properly, proper care. Now let's get into energy in magnetic fields. Okay, so I have taken the inductance route. So let me look at the circuit route first. Okay, so we need to do work to start a current in a circuit. We said that, right? So to set a current going, work must be done against the back EMF. Okay, that gives rise to stored but recoverable energy. Unlike energy in a, if you have a current in a resistor, that the energy lost is I square R. That is lost energy. Okay. But in a capacitor, in an ideal capacitor, if you charge, you store electrical energy. Okay. But here I'm not taking the inductor. I'm taking any circuit. Okay. So if now you have to set a current in that circuit, you have to work against the back EMF that we have just seen because of the self inductance. Okay, so that stores, but you are doing work, and where does that work go? Work doesn't go west against the back EMF. That is stored as recoverable energy. All right. So the work done to push charge, what is the amount IDT in small dt time? What is the amount of charge that will be dq? Dq is IDT, but we'll be working against back EMF, let's say E. And so the differential work done would be, of course, we're working against, okay, so minus EMF IDT is the charge work done. And hence I can write down that dW by dt, the rate of doing work, would be minus EMF I, and we know what is EMF is minus LdA by dt. So dW by dt is minus ILdA by dt, and hence I can calculate from W by integrating W from wherever, from setting up my, let's say starting from zero current to set up I, the total I. Okay, we can ramp up the current to I, and that would give us the total work done as half Li square. Okay, so that is I di integral. Okay, that is the work done is half Li square. And so that is, it does not depend on the rate of at which you do it. That is from 0 to I, how fast you go. Okay, the fact that you go till I, that's an integral. So it depends only on L. All right. So half Li square. So this is quite a general argument, and you are familiar with this from the circuit point of view. For an ideal inductor, that is the magnetic energy stored is half Li square. All right. So it stores magnetic energy as just as a capacitor stores electrical energy. Okay, in a conductor. But this argument is not dependent. I am not talking only about one ideal inductor. I'm talking about any circuit. Okay, so this is so energy. This from circuit point of view, but we have been doing from field point of view. So let's look at magnetic energy from the field point of view in terms of field variables. Okay, uh, that is, we know that total flux is B going through an area dA, so B dot dA. But B I can always express as del cross A. Okay, that we know, dot dA, and convert it through Stokes theorem to line integral of A dot dl. Few slides back I just did that. Okay, so the flux is line integral of A dot dl. All right, knowing that, so I can know that, but the flux is also L into I. All right, so I can, so this is a potential, line integral of the potential. So W, then I can say that half I A dot dl. All right. Okay. So that is a quite a nice formula for calculating the work done in setting up a current I. Okay, I can generalize this. This is for a line current, but I could generalize this to a volume current instead of I, let's say J. Then there's of course A dot J. Okay, I could have taken this I and made this DL as I vector, but I normally don't write as a vector. Okay, so W is equal to half A dot J d tau. All right. So that is my generalized work in terms of vector potential. So, but then J, I can always express as del cross B by mu naught, right? That's Ampere's law. Okay. So, del cross B by mu naught. So, this integral over the volume of that. This more general. Now, A dot del cross B, that immediately tells us that I could use the integration of by parts, okay, using a certain product rule of dot and cross. So if I know that this is the product rule 6, okay, I think this is if I have the del dot A cross B, then B dot del cross A and minus A dot del cross B. Okay, so what we have here is A dot del cross B. All right, so I could write down A dot del cross B is equal to now I have taken this out here and this back here, right? Because I want to partially do the partial integration on terms of A dot del cross B, all right? But del cross A itself is B. So this term is B dot B or B square, all right? So this integral I can write down as W half 1 by 2 epsilon naught. The first term becomes B square d tau minus this term, okay? That is del dot A cross B d tau. All right. So W is then the work done is then of course I can convert this volume integral into a surface integral. Okay. So this is divergence theorem, divergence of A cross B. Okay. I can call it A cross B dot dA. And so this is a volume integral, and for the same volume I have a surface integral, the surface of the volume. All right. So this is the same old trick that we had done even earlier in electrostatics. Okay, the same argument except with B. Okay. So this I can say that this is localized current J. J is a localized current. So if I go and enclose it with a volume, and that volume includes already all the J, then doesn't matter how large the volume I, because J outside is 0, so I can keep on increasing the volume of over which I integrate. Okay, and then if I do a very large of all space, then this is a surface integral. The surface goes to the size of the volume. The surface goes to infinity, and then of course the contribution of this quantity goes to 0. Exactly the same argument we have used earlier. Okay, so if I integrate over all space, and I can always do that because my J is some localized current. All right, so I have, as long as I take all space, and so contribution from all J's outside that localized current is 0. Okay, and hence I can integrate 1 by 2 I mean all space B square d by tau, and that is the work done. Okay, so magnetic energy stored in a B field is that. Okay, so if we integrate for all space, the surface integral goes to 0, as I've just argued. All right, but magnetic fields do no work. So why work is needed to create it? Okay, that's a natural question. Magnetic field, we have said, never do any work. But to create the magnetic field itself, we have to work. Why is that? That's because only Faraday's law can explain it. So while magnetic field is changing, I'm changing, right? Okay. So you are building it up. So it induces, because it's changing, it induces electric field. And you are actually working against that electric field needs to be work done, exactly like back EMF to store it. Okay, so in the whole problem, there is no E to start with because you started with 0 magnetic field and you have ended up with magnetic field B. Okay, there is no E anywhere inside, but going from 0 to B in setting it up, okay, you have to work against the induced electric field, and that you have to work against, and hence that is the work that gets stored in the magnetic field. All right. Now, we have seen that the W magnetic is 1 by 2 mu naught over all space B square d tau. And we have seen that I can express it in terms of A dot J d tau. So they are the two relevant formulae for this, the very general formula, and this is for in terms of the field coordinates B. This is in terms of potential and the source, and this is in terms of field. Isn't this very similar to what we have seen in electrostatics also? Let me remind you that. So the electrical energy stored is half of potential into the source rho d tau. Okay, and so similar in terms of field quantities, the energy stored is epsilon by 2, okay, E square d tau all space. So exact similarity, okay, one to one similar between the two. One must note that. All right. I had not written down here. So this is, we did it by transferring the derivative from B to A using integration of parts with the help of product rule 6. I think I was trying to and remember the product rule number in your book is product rule 6, and that's this derivation. Once I tell you that this is the derivation, you'll be able to go through. All right, because it's exactly the same. We have done it many times over. How to convert this from a volume integral to surface integral, and how to now make a comparison between the volume and surface, and let the surface blow up to go to such that the contribution of the surface goes to zero, and that's the trick that we did. So I have shown you. I did this at this point of time because of the Faraday's law was necessary to figure out why were you doing work. All right. And the magnetic energy through, first I came through the circuit route, okay, that is L, inductance, and then we could convert that into field terms, in terms of field variables. All right. So let's take a quick example. This is let's take this most practical example. A long coaxial cable, that is what normally you use to connect one instrument to another. So, and then of course the current flows down the surface of the inner cylinder, okay, of radius, let's say A, and back along the other cylinder B. We have done problems of this nature in calculating magnetic field B. Now the question is, find the magnetic energy stored in a section. This is a long cable, so in a section of length L, okay, and they calculate the self-inductance of the cable. It's a simple problem, but with an important problem. So the field between the cylinders, okay, we have done it earlier in a problem or an example. So using an Amperian loop, I can always write down mu naught I 2 pi s in the phi direction. So current is axial, and hence magnetic field is circumferential. And the symmetry Amperian loop can be used, and that is mu naught by 2 pi s phi. All right. So that is, and zero elsewhere, right? Because this I and this I both feel as if there is a current at the center. So this zero elsewhere is only between these two, there is the magnetic field. So what is the energy per unit volume? Okay. So I'm saying that magnetic energy Wm, small w, okay, per unit volume, and that's why I'm saying small case. Okay, so that is 1 by 2 epsilon naught b square, okay, per volume. So mu naught I square 8 pi square s square, and I know b. Okay, so energy in a cylindrical shell of length L and radius S, and let's say thickness ds. Okay, because I want to calculate the total energy inside it. Okay, so I'll have to just integrate. Okay, so this is 2 pi SL ds is the volume. So this is the total per unit volume, and the volume is 2 pi SL ds for a small section here. And hence, if I get it as in terms of ds by s, now I integrate s from A to B to obtain the total energy stored in this. Okay, so let's say integrating from A to B, I get W is mu naught I square L by 4 pi, and of course ds by s from A to B gives me log of B to A. So So total energy stored in terms of I square. Okay, I square L. So now, but I know that W is equal to half Li square, and here is I square, and hence I can say that what is L directly from here. Okay, all right. So that's my L. So this is quite a neat way of getting L through magnetic energy, and this method uh, is of finding inductance is convenient in many cases when here the current is going to infinity. Okay, when the loops are spread out, and the flux calculation is are different, or there might be a circuit in which different parts of the circuit is entertaining different kind of fluxes, magnetic flux. So in that case, it is difficult to do work through the circuit element that we did that in terms of L, but it is easier to go through the energy stored, and this is half Li square if you can energy stored, and then from that you can get L. So that's quite a neat way of doing that. So we have done now uh, electrostatics, magnetostatics, and have gotten all the laws under our belt, and we'll now take up the Maxwell's equations in full blown all Maxwell's equations. Okay, so that's in the next lecture.